All right, today we are looking at 7-6 notes. So we're shifting over from triangle congruent properties. We're going to take a look at some parallelograms. So a little bit of review of first semester as well, just to make sure we're ready to go. We're going to start with reviewing properties of parallelograms. So the first thing to make something a parallelogram, it just has to have opposite sides that are parallel. With that, though, we can make the property that opposite sides are parallel and congruent. That should be congruent. So if we take our parallelogram on the right here, and we can actually put those notations in. So opposite sides have to be parallel. And congruent. Second property, opposite angles are going to be congruent and adjacent angles are supplementary. So I could say opposite angles are congruent and we know adjacent angles, these two have to be supplementary, which means they're going to add to 180 degrees. Third property, that the diagonals are going to bisect each other. Okay, so I'm going to draw in some diagonals here. I know diagonals bisect each other, so these are going to be congruent, and these pieces are going to be congruent. Good, so if we think about that hierarchy of quadrilaterals back from chapter 4, think about what other quadrilaterals fell below parallelograms. And so we can actually say that rhombuses, rectangles, and squares are also going to have the same properties as parallelograms. All right, we have two theorems for parallelograms, and then we're going to kind of just go through some examples on using all of these properties and these theorems. So the first theorem that we have is called the parallelogram distance theorem. It is saying that the distance between opposite sides is constant, so it always has to be the same, and we always measure that distance at a perpendicular. Okay, so it's saying if I draw the distance between these, this is going to have to always be perpendicular to the bases that we're talking about. And it doesn't matter where I draw this, right? Anywhere on here, if I draw this and it's perpendicular, these should always be the same. That includes if I were to draw the height or the altitude out here. If I continue this with a dashed line, this would be 90 degrees and 90 degrees. These all have to be constant. They all have to be congruent to one another. Our second theorem then is rotational symmetry theorem. So a little review of that chapter 4 again. So every parallelogram has twofold rotational symmetry from its center. Okay, so we're going to mark the center. The center is going to be wherever the diagonals intersect. Okay, that's going to be your center. And it's just saying it has twofold rotational symmetry, which means when you rotate it 2 times before it gets back to its original, it looks like itself. Okay, some examples. So our first one. In the parallelogram at the right, we're going to add point X where the diagonals intersect. So this is now going to be our center here where they intersect. And we want to label all congruent segments in the diagram. I'm going to start by labeling the actual segments from the parallelogram that are congruent. Okay, so we know AD is congruent to BC, AB is congruent to DC. Then we also look at the diagonals. We know AX has to be congruent to XC. We know DX has to be congruent to XB. Says what is the n-fold rotational symmetry? Right, we just wrote down in our theorem that this is going to be twofold. If I want to find the magnitude again, we just always divide 360 by what the n-fold is. So this magnitude would be 180 degrees. Some examples, we have some always, sometimes, never questions. So a parallelogram, blank has rotational symmetry. That is going to be always. Right? We can rotate it 180 degrees and it'll turn back to looking like it did originally. The distance between parallel lines, that is always going to be the same. So we just drew that in with our perpendicular lines in that theorem. Those will always be the same. And then it says the diagonals of a parallelogram are blank congruent. That would be sometimes. In a regular parallelogram, they aren't. But if we look specifically at a rectangle or a square, then we know that the diagonals are going to be congruent. So we would put sometimes for that. All right, a little algebra review. So it says in parallelogram QWHD at the right, we know that the length of DK is 3x minus 7. We know the length of DW, so this whole thing, is 16. We want to find the value of x. Couple options here. We know these have to be congruent. The diagonals bisect each other. So you could also write this as 3x minus 7, and you could add those up to equal 16. Possibly a little faster algebraically is that I could just multiply 3x minus 7 by 2. That has to also equal the entire length of 16. So I use my distributive property, add 14 over, and we should get that x equals 5. All right, 2 more problems, 2 proofs that we're going to take a look at. So here I have the given is just that ABCD is a parallelogram. So now we can pull from all of those properties that we wrote down on the first page of notes to try to figure out which one's going to help us to prove that angle 1 is congruent to angle 4. So the first thing I'm actually going to use is the fact that we know that angle 1 and 2 have to be congruent because they are opposite angles in a parallelogram. So I'm going to go and say angle 1 is congruent to angle 2. That is going to be by the definition of a parallelogram. Then we go back to chapter 2 material. We know 2 and 4 are going to be congruent. By vertical angle theorem. And then we also go back to some of our earlier proofs. If I have 3 things that are congruent, remember in order to take out that repeating piece, we can use the transitive property. So now I can say angle 1 is congruent to angle 4 by the transitive property. All right, let's try the last one. Same given. So I know that the ABCD figure given is a parallelogram. Now the goal is that I want to try to prove that these 2 triangles are going to be congruent. Okay. So the first thing I'm going to take a look at is if I know it's a parallelogram, I know opposite sides have to be congruent. So I can mark those on here, and then I need to make the statements in my proof. So I'm going to go AD has to be congruent to BC. And I also know AB has to be congruent to CD. Both of these, I'm going to summarize them together. Both of these are by the definition of a parallelogram. Okay, and then we have some options. Okay, so I'm going to kind of do an or situation here. So from here down, right, step 4, I could take a look at this picture and realize that they share a common side. And so I could say that BD is congruent to itself. By the reflexive property. And if I know that and I look at my picture, then I know that the triangles are congruent by side, side, side. So then I can say triangle ADB is congruent to triangle CBD by side, side, side. So that is an option, right? Then we've proven. Now, or step 4, I could have said that these opposite angles are congruent. Okay, because this is a parallelogram, I know that angle A would be congruent to angle C. That would also be by the definition of parallelogram. And then for step 5, I could say the triangles would be congruent. Instead of side, 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 this would be side, angle, side. So either one is fine, it doesn't matter. They both prove that the triangles are congruent.